Hello there, and welcome to this gentle corner of the microscopic world, where the universe's tiniest building blocks get wrapped in wonder and curiosity takes a thoughtful stroll through the infinitely small. Tonight's peaceful journey is all about something we learnt about in school, but perhaps never truly understood. The atom, that fundamental piece of everything that makes up you, me, and every single thing we've ever touched or seen. Right now, as you're watching this, trillions upon trillions of these invisible architects are dancing together to create your skin, your breath, even the light reaching your eyes. Yet if you could somehow zoom in close enough, you'd discover they're mostly empty space, a mystery that would make the greatest magicians jealous. But before we unravel the elegant puzzle of what atoms really are, I'd love to know, where in the world are you watching from, and what time is it for you right now? Fitting, isn't it? Here we are, scattered across time zones, each of us made of countless atoms, contemplating the very nature of atoms themselves. If you find this voyage soothing, intriguing, or just a nice way to unwind after a long day, I'd be ever so grateful if you gave the video a like, and maybe subscribed. It helps this little corner of calm reach others who might need a peaceful pause with the universe's most fundamental questions. Now, I do hope this isn't so fascinating that it keeps you awake pondering the building blocks of existence, but if it does, well, at least you'll drift off knowing something remarkable about the invisible choreography happening within every fiber of your being. So, settle in, slow your thoughts, and let's begin, because somewhere between the vast emptiness and the vibrant dance of particles, between what we think we know and what atoms actually are, lies one of nature's most beautiful secrets. Have you ever stood in front of a mirror and wondered what would happen if your reflection could step out and shake your hand? Not the glass version of you, but something that looks exactly like you, yet is fundamentally opposite. That handshake might be the last thing either of you ever does. This isn't science fiction. It's the story of antimatter, the universe's most dangerous substance, born in the very first moments after the Big Bang. Imagine the universe as a newborn, barely a trillionth of a second old, when energy was so intense, it could spontaneously create pairs of particles. But here's the cosmic joke. For every particle of matter that popped into existence, an antiparticle appeared alongside it, like a shadow that could destroy its owner. In those first moments, the universe was perfectly balanced on a knife's edge, equal amounts of matter and antimatter dancing together in the cosmic soup. If you could have witnessed it, you might have seen the most beautiful and terrifying light show imaginable, particles and antiparticles meeting, annihilating each other in perfect flashes of pure energy, only to be replaced by new pairs born from that same energy. The temperature was so extreme that even photons, particles of light, carried enough energy to split apart and create matter-antimatter pairs. It was like a cosmic nursery where creation and destruction happened simultaneously, billions of times per second. Every particle that came into being brought with it its own potential destroyer. But something went wrong with this perfect balance. Or perhaps, from our perspective, something went magnificently right, because if that balance had been maintained, if a particle of matter had found its antimatter partner, the universe would have annihilated itself in a brilliant flash, leaving nothing but photons racing through empty space forever. Instead, for every billion antimatter particles, there were 1,000,000,001 matter particles. Just one extra particle of matter for every billion pairs. That tiny, almost negligible imbalance, less than a rounding error in cosmic accounting, is why you exist, why Earth exists, why anything exists at all. The rest of the antimatter, it met its match and vanished in the greatest fireworks display the universe has ever seen, converting into the cosmic microwave background radiation that we can still detect today, the afterglow of annihilation that fills every corner of space like a whisper from the universe's violent birth. Think about the last time you looked in a bathroom mirror while brushing your teeth. Your reflection raised its left hand when you raised your right. Simple, predictable, safe. But what if I told you that nature has its own mirror, one that doesn't just flip left and right, but flips the very essence of what things are? In the world of particle physics, this mirror is called charge conjugation, and it's far more unsettling than any funhouse reflection. When you peer through this invisible mirror, electrons become positrons, protons become antiprotons, and every fundamental building block of reality gets turned inside out, while maintaining its essential character. An anti-electron, we call it a positron, has the same mass as an electron, the same spin, the same size, but its electric charge is positive instead of negative. It's like meeting someone who looks exactly like you, thinks like you, walks like you, but every fundamental aspect of their being is perfectly opposite to yours. This isn't just a curiosity, it's a fundamental symmetry of the universe, discovered when physicists realized that the equations describing particle behavior remain perfectly valid when you swap every particle for its antiparticle. It's as if the universe is ambidextrous, equally comfortable with matter or antimatter as its primary ingredient. Paul Dirac, the brilliant physicist who first predicted antimatter's existence, found it hiding in his equations like a secret message. In 1928, he was trying to marry quantum mechanics with Einstein's relativity, and his mathematics kept insisting that for every solution describing a particle, there had to be another solution describing something else, something with opposite charge but identical mass. At first, Dirac thought these solutions were just mathematical ghosts, meaningless artifacts of the equations, but nature, it turns out, is rarely wasteful with mathematical beauty. When something is mathematically possible and elegant, the universe often finds a way to make it real. The first positron was discovered in 1932 by Carl Anderson, captured in a cloud chamber photograph that looked like the track of an electron but curving the wrong way in a magnetic field. It was matter's shadow made visible, the first glimpse of the mirror universe that surrounds us. But here's what makes this mirror particularly haunting. Unlike your bathroom reflection, if you ever touched your antimatter mirror image, you wouldn't just see your reflection disappear. You'd both vanish in a flash of energy, so pure and complete that even Einstein's famous equation E=mc² couldn't fully capture its violence. This is the universe's ultimate magic trick, creation and destruction happening simultaneously, perfectly balanced, leaving nothing behind but energy racing away at the speed of light. Remember playing on a perfectly balanced seesaw as a child, that moment when you and your friend were exactly the same weight, suspended in perfect equilibrium, neither going up nor down. The universe started on a cosmic seesaw just like that, with matter on one side and antimatter on the other, perfectly balanced. Every law of physics we know suggests this balance should have been maintained. Conservation of energy, conservation of electric charge, conservation of momentum, all the fundamental rules that govern reality, seem to demand that when you create a particle, you must create its antiparticle partner. It's like a cosmic accounting system where every entry requires an equal and opposite entry to balance the books. In particle accelerators today we see this symmetry in action. When we crash particles together at tremendous speeds, they shatter into showers of new particles, but always in perfectly matched pairs. Create an electron, and you must create a positron. Create a quark, and you must create an antiquark. The universe seems to be meticulous about keeping its accounts balanced. This symmetry runs deeper than just electric charge. There's a beautiful mathematical principle called CPT symmetry, charge conjugation parity and time reversal, that suggests the laws of physics would remain unchanged if we simultaneously flipped every particle to its antiparticle, mirrored space like a reflection, and ran time backward. It's as if the universe has a perfect twin, running in reverse, made of antimatter. Yet here we are, in a universe dominated by matter, where antimatter has become the rare exception rather than the equal partner. It's as if we're living on a seesaw where one side mysteriously became heavier, but we can't figure out how or why. The standard model of particle physics, our best theory of how the universe works at its most fundamental level, contains some subtle violations of this perfect symmetry. There are rare processes where particles can decay in ways that slightly favor matter over antimatter, like a cosmic loaded dice that comes up heads just slightly more often than tails. But these violations are incredibly small, far too small to account for the dramatic imbalance we observe. To explain why our universe is made of matter, we need something that violated matter-antimatter symmetry by about 1 part in a billion. The violations we've discovered so far are more like 1 part in 1,000 billion. It's as if we're trying to explain why the ocean is salty by pointing to a single grain of salt. The math doesn't add up, leaving us with one of the most profound mysteries in physics. Why is there something rather than nothing? Why did matter win the cosmic battle against antimatter? This question keeps physicists awake at night, not because they're afraid of the dark, but because they're afraid of the light, the blinding flash of understanding that might reveal whether our existence is a lucky accident or the inevitable result of laws we haven't yet discovered. Have you ever lost something important and retraced your steps, trying to figure out where it could have gone? Now imagine losing half of everything that ever existed, and you'll begin to understand one of the universe's greatest mysteries. Somewhere in the first second after the Big Bang, the universe lost almost all of its antimatter, not misplaced, not hidden, completely annihilated, converted into energy and lost forever. It's the largest disappearing act in cosmic history, and we're still trying to figure out how the trick was performed. The evidence for this cosmic crime scene is written in the stars themselves. When we look out at the universe, we see galaxies made of matter, stars burning matter, planets built from matter. If there were substantial amounts of antimatter out there, we'd see the characteristic gamma rays produced when matter and antimatter meet at the boundaries between regions. But space is surprisingly quiet, suggesting that antimatter has been almost completely eliminated from the cosmic neighborhood. This disappearance happened fast within the first few minutes of the universe's existence. During those early moments, the universe was hot enough and dense enough that particles and antiparticles were constantly being created and destroyed. It was like a cosmic dance floor where partners kept switching, creation and annihilation happening in perfect rhythm. But then, something shifted the music. Some process, some asymmetry began to tip the balance ever so slightly in favor of matter. For every billion antimatter particles that found their matter partners and annihilated, there was one lone matter particle left standing, like the last dancer when the music stopped. As the universe expanded and cooled, this process came to an end. The temperature dropped below the threshold needed to create new particle-antiparticle pairs, and the cosmic dance floor went quiet. The surviving matter particles, roughly 1/1000th of the original population, became the seeds of everything we see today. The energy released from all that annihilation didn't just disappear. It became the cosmic microwave background radiation, the afterglow of the universe's birth that we can still detect today. Every photon in this background radiation carries a tiny piece of the story of antimatter's disappearance, like forensic evidence from a cosmic crime scene. Scientists have proposed several theories for what might have caused this great imbalance. Maybe there are unknown particles that decay differently into matter and antimatter. Maybe the laws of physics themselves have a subtle preference for matter over antimatter. Maybe there are hidden dimensions where antimatter physics works differently. But the honest answer is that we don't know. We're cosmic detectives investigating a case where the crime happened 13.8 billion years ago. The evidence has been scattered across the universe, and the perpetrator might be the laws of physics themselves. What we do know is that this disappearance was necessary for our existence. If matter and antimatter had remained perfectly balanced, they would have annihilated each other completely, leaving a universe filled with nothing but light. No atoms, no molecules, no stars, no planets, no life. Just photons racing through empty space for eternity. Picture the most complete destruction you can imagine. Not just something breaking apart or burning up, but something disappearing so completely that it's as if it never existed at all. That's what happens when matter meets antimatter. Not destruction, but true annihilation, where two things become nothing, leaving behind only pure energy. This process is governed by what we might call the law of annihilation, though it's really just Einstein's famous equation E-O, taken to its logical extreme. When a particle meets its antiparticle, they don't just cancel each other out, they transform completely into energy, releasing every bit of their mass, according to Einstein's formula. The amount of energy released is staggering. If you could annihilate just 1 gram of matter with 1 gram of antimatter, you'd release about 180 terajoules of energy, roughly the same amount as the explosion of 43,000 tons of TNT. That's more energy than the atomic bomb dropped on Hiroshima, all from 2 grams of material that you could hold in your hand. This isn't like burning wood or exploding dynamite where chemical bonds are broken and reformed. This is the complete conversion of matter into energy, the most efficient reaction possible in the universe. Nuclear fusion, the process that powers the sun, converts less than 1% of mass into energy. Antimatter, annihilation, converts 100% of mass into energy. The process happens with a kind of mathematical perfection that would make poets weep. When an electron meets a positron, they spiral into each other and vanish, replaced by 2 gamma rays racing away in opposite directions. The energy is divided equally between them, and they carry it away at the speed of light, as if the universe is determined to conserve not just energy, but also momentum and symmetry. The gamma rays produced by annihilation are distinctive. They have a specific energy signature that scientists can detect and identify. It's like a cosmic fingerprint, proof that annihilation has occurred. When we see these gamma rays in space, we know that somewhere, matter and antimatter have met and danced their final dance. This annihilation happens instantly, faster than any chemical reaction, faster than any nuclear process. The particles don't have time to struggle or resist, they simply cease to exist, replaced by energy that will travel across the universe until it's absorbed by something else, carrying the news of their mutual destruction. But here's the beautiful and terrible symmetry of it all. Annihilation is also creation run backward. Just as energy can spontaneously create matter-antimatter pairs under the right conditions, those same pairs can spontaneously return to pure energy. It's as if the universe is constantly borrowing mass from its energy bank account, sometimes paying it back with interest. This process has been going on since the first moments after the Big Bang, and it continues today in particle accelerators, in the upper atmosphere, where cosmic rays create brief showers of particles and antiparticles, and in the cores of stars where high-energy processes occasionally produce antimatter that immediately annihilates with surrounding matter. It's happening right now in your body, where radioactive decay occasionally produces positrons that annihilate with electrons in your cells, contributing to the natural background radiation that surrounds us always. You are, in a very real sense, a tiny antimatter factory, constantly creating and destroying these mirror particles as part of the natural processes that keep you alive. There's something profoundly unsettling about perfect efficiency. When you burn a log in a fireplace, you get heat and light, but you also get ash and smoke, remnants that prove something was there. When matter and antimatter annihilate, they leave nothing behind except pure energy. It's as if they never existed at all. This completeness is what makes antimatter so dangerous, but also so fascinating. In a universe where nothing is ever truly destroyed, only transformed, annihilation represents the closest thing to absolute negation. Two particles become zero particles, and the only evidence of their existence is the energy that races away at the speed of light. The energy released is so pure it's almost abstract. Gamma rays with no mass, no charge, no substance beyond their ability to carry energy from one place to another. It's as if the universe is speaking in its most fundamental language, converting the solid reality of matter into the ethereal language of light. Scientists have calculated that if we could somehow collect all the antimatter that naturally exists in the observable universe, it would weigh less than a paperclip. Yet this tiny amount of antimatter, if brought together with an equal amount of matter, would release enough energy to power human civilization for millions of years. It's the ultimate example of quality over quantity, a substance so powerful that its scarcity is probably the only thing that keeps us safe. This power has not gone unnoticed. Science fiction has long imagined antimatter as the ultimate weapon, the perfect fuel, the key to traveling between stars. But the reality is more complex and more dangerous than fiction usually portrays. The same perfect efficiency that makes antimatter so appealing also makes it nearly impossible to control. There's no antimatter equivalent of a safety switch or a control rod. When matter and antimatter meet, they annihilate whether you want them to or not. There's no way to make the process go slower, no way to dial down the energy release, no way to change your mind once the reaction begins. It's like trying to negotiate with the laws of physics themselves. This absolute nature of annihilation gives antimatter a kind of cosmic authority. It doesn't care about your intentions, your engineering, or your safety protocols. It follows its own rules, with the implacable certainty of mathematics, converting matter to energy with the same reliability that 2 + 2 = 4. The gamma rays produced by annihilation are so energetic they can pass through solid matter almost as easily as light passes through glass. They're invisible, untouchable, and incredibly penetrating. When antimatter annihilates, it doesn't just release energy, it releases energy that can travel through almost anything, carrying the news of destruction far beyond the point where it occurred. This is why antimatter represents such a unique challenge to human technology. We've learned to harness nuclear energy, to control chemical reactions, to manipulate electricity and magnetism, but antimatter operates on a level of energy and efficiency that makes our other technologies look like stone tools by comparison. The power of nothing left behind is not just about the energy released, it's about the completeness of the transformation in a universe where matter is conserved, where energy is conserved, where information is conserved. Annihilation represents the closest thing to true deletion. 2 particles enter, 0 particles leave, and only energy remains to tell the tale. Imagine trying to catch a fish that dissolves the moment it touches water, or hunting for a shadow that disappears when light hits it. That's what it's like for scientists trying to study antimatter, a substance that destroys itself the moment it encounters the matter-filled world we live in. The challenge is profound. How do you study something that can't exist in the same space as your instruments? How do you observe something that annihilates the moment it comes into contact with the matter that makes up your detectors? It's like trying to photograph a vampire. The very act of observation threatens to destroy what you're trying to study. Scientists have become incredibly creative in their ghost hunting techniques. They've learned to create antimatter in tiny quantities, trap it in magnetic fields, and study it for brief moments before it inevitably encounters matter and vanishes. It's like creating lightning in a bottle, except the lightning is made of the most dangerous substance in the universe. The process usually starts in particle accelerators, massive machines that smash particles together at incredible speeds. In these collisions, energy converts back into matter-antimatter pairs, just like in the early universe. But instead of the cosmic chaos of the Big Bang, scientists create controlled crashes, producing antiparticles one at a time in carefully designed experiments. Catching these antiparticles is like trying to catch soap bubbles in a hurricane. They're created moving at tremendous speeds, and they immediately begin looking for matter to annihilate with. Scientists use magnetic fields to bend their paths, electric fields to slow them down, and laser light to cool them to temperatures just above absolute zero. The magnetic traps used to hold antimatter are marvels of engineering. Invisible cages made of precisely controlled magnetic fields that can hold antiparticles without any physical contact. The antiparticles float in these traps like genies in bottles, held suspended by forces that push them away from the walls without touching them. Even then, the antimatter doesn't last long. Antihydrogen atoms, the simplest form of antimatter, can be held in these traps for only minutes at a time. Compare that to regular hydrogen atoms, which can exist for billions of years. It's like comparing a candle flame to the sun. Both are made of the same fundamental processes, but one is inherently fleeting while the other seems eternal. The detectors used to study antimatter are equally ingenious. They're designed to capture and analyze the gamma rays produced when antimatter inevitably annihilates, reading the energy signatures like forensic scientists examining evidence from a crime scene. Each annihilation event tells a story about the antimatter that was briefly created and immediately destroyed. Sometimes scientists get lucky and natural processes create antimatter for them to study. Cosmic rays hitting the atmosphere occasionally produce antiparticles that scientists can detect before they annihilate. Lightning strikes can create positrons in the electrical chaos of a thunderstorm. Even bananas produce antimatter, about one positron every 75 minutes from the radioactive decay of potassium-40. But these natural sources are unpredictable and uncontrollable. To really study antimatter, scientists need to create it on demand, in controlled conditions, where they can probe its properties and test whether it behaves exactly the same as ordinary matter. It's like trying to study a rare species of butterfly by catching one at a time, examining it briefly, and then watching it disappear forever. The irony is that antimatter is simultaneously the most dangerous and the most fragile substance we know. It can release tremendous amounts of energy, but it can't survive contact with the ordinary matter that makes up our world. We're ghost hunters pursuing something that's incredibly powerful but utterly ephemeral, chasing shadows that could light up the world if only we could catch them. Think about trying to store a flame without fuel, or keeping ice frozen without cold. That's the challenge scientists face when trying to store antimatter. How do you keep something that destroys itself the moment it touches anything solid, liquid, or gas? The solution is to create traps made of nothing but force fields, invisible cages woven from magnetic fields, and electric fields that can hold antiparticles without any physical contact. These traps are like bottles made of light containers that exist only in the mathematics of electromagnetic fields. The most common type is called a Penning trap, named after Franz Penning, who developed the technique in the 1930s. Imagine a saddle-shaped valley made of electric fields, with magnetic fields providing walls that curve in 3 dimensions. Antiparticles can be suspended in this valley, held in place by forces that push them away from the walls without ever touching them. The precision required is staggering. The magnetic fields must be stable to within 1 part in a billion. The electric fields must be perfectly aligned and the entire apparatus must be kept at temperatures just above absolute zero. It's like trying to balance a soap bubble on the tip of a needle while riding a roller coaster. Any vibration, any fluctuation, any imperfection can cause the antimatter to touch the walls and annihilate. Scientists at CERN, the European Organization for Nuclear Research, have built the most sophisticated antimatter traps in the world. Their alpha experiment can hold antihydrogen atoms for up to 1,000 seconds, about 17 minutes. To put that in perspective, an antihydrogen atom moving at room temperature would travel about 100 meters in that time. They've essentially created a box, smaller than a refrigerator, that can hold the most dangerous substance in the universe for as long as a coffee break. The traps themselves are works of art as much as science. They're made of precisely machined electrodes, superconducting magnets, and laser systems that can manipulate individual atoms. The entire apparatus is kept in ultra-high vacuum, with pressure so low that the few remaining gas molecules are millions of times more sparse than the air at the top of Mount Everest. But even these sophisticated traps can't hold antimatter indefinitely. The antiparticles gradually lose energy through interactions with the electromagnetic fields that hold them, and eventually they drift into the walls and annihilate. It's like trying to keep a ball balanced on a hill. You can do it for a while with careful adjustments, but eventually gravity wins. The amount of antimatter that can be stored is vanishingly small. The most successful experiments have held fewer than 1 million antiprotons at a time. Sounds like a lot, but it's actually only about 0.0000000 grams of antimatter. If you could somehow collect all the antimatter ever created and stored by humans, it wouldn't be enough to power a light bulb for a few minutes. This storage problem is one of the main reasons why antimatter remains primarily a scientific curiosity rather than a practical technology. It's like trying to build a solar panel that only works in complete darkness. The fundamental physics makes it nearly impossible to scale up to useful quantities. Some scientists have proposed exotic storage methods, using magnetic bottles in space, where the vacuum is naturally perfect and there's no matter to interfere with the traps. Others have suggested using crystalline structures that could theoretically hold antimatter in stable configuration. But these ideas remain purely theoretical, limited by our current understanding of physics and engineering. The traps of light that scientists have built represent humanity's most ambitious attempt to domesticate the impossible, to take the most dangerous substance in the universe and make it sit still long enough for us to study it. They're monuments to human ingenuity, proof that we can sometimes outsmart the laws of physics through cleverness and precision. But they're also humbling reminders of how much we don't know. Every antimatter trap is a temporary victory against the fundamental forces of nature, a brief moment when we can hold something that the universe seems determined to destroy. A gram of sugar can sweeten your coffee. A gram of salt can season your dinner. A gram of antimatter can level a city. Welcome to the terrifying mathematics of E = mc², where tiny amounts of mass can release unimaginable amounts of energy. Let's put this in perspective. A gram of matter meeting a gram of antimatter releases about 180 terajoules of energy, equivalent to about 43,000 tons of TNT. That's roughly 3 times the energy of the atomic bomb that destroyed Hiroshima, from just 2 grams of material that would fit on a teaspoon. This isn't theoretical, the physics is well understood, the mathematics is precise, and the potential for destruction is absolute. Unlike nuclear weapons, which convert less than 1% of their mass into energy, antimatter annihilation converts 100% of mass into energy. It's the most efficient explosive reaction possible in the universe. The energy release happens instantly, faster than any chemical reaction, faster than any nuclear process. There's no chain reaction to interrupt, no critical mass to avoid, no way to make it go slower. When matter and antimatter meet, they annihilate whether you want them to or not, releasing their energy in a burst of gamma rays that can penetrate almost any shielding. But here's what makes antimatter particularly dangerous. It's not just the energy that's released, but the form that energy takes. The gamma rays produced by annihilation are incredibly penetrating, capable of passing through meters of concrete or steel, unlike a conventional explosion, which you might survive by being far enough away or behind thick enough walls. Gamma rays can find you almost anywhere. The radiation dose from a single gram of antimatter annihilating would be lethal to anyone within several kilometers, even if they were inside buildings or underground. It's like a nuclear explosion without the mushroom cloud. Pure, penetrating radiation that spreads out in all directions at the speed of light. Scientists have calculated that if someone could somehow detonate a gram of antimatter in the center of Manhattan, the gamma radiation would be instantly fatal to everyone within about a 1.5-kilometer radius. People up to 10 kilometers away would receive doses that would kill them within days or weeks. The economic damage would be in the trillions of dollars, and the area would remain dangerously radioactive for years. This is why antimatter has been called the perfect weapon. No radioactive fallout to contaminate the environment permanently, no complex delivery systems required, no uranium or plutonium to enrich, just the complete conversion of matter to energy. Clean and efficient and absolutely devastating. But the same properties that make antimatter so dangerous also make it almost impossible to weaponize. That single gram of antimatter would need to be stored in perfect vacuum, held in place by magnetic fields, and kept away from any matter whatsoever. The storage system would be larger than most buildings, require enormous amounts of power to maintain, and would be incredibly fragile. Current technology can create antimatter only in quantities measured in individual atoms. To produce a gram of antimatter using today's methods would require more energy than the entire world produces in a year, and would take millions of years to accumulate. It's like trying to fill a swimming pool with an eyedropper, theoretically possible, but practically impossible. The danger isn't in someone building an antimatter bomb. It's in someone accidentally creating larger quantities of antimatter than they can safely handle. As our technology improves, as we learn to create and store antimatter more efficiently, we need to be incredibly careful about the quantities we work with. Even tiny amounts can be dangerous. A microgram of antimatter, 1/1,000,000th of a gram, barely visible to the naked eye, would release as much energy as a hand grenade. A milligram would be like a small bomb. There's no safe way to handle these quantities without perfect containment systems. The danger of a single gram reminds us that some knowledge comes with terrible responsibility. We're learning to manipulate the most powerful forces in the universe, forces that were present at the creation of everything we know. The same physics that explains why stars shine and why we exist also explains how to release more energy than any conventional weapon ever built. There's something deeply unsettling about the idea that the fundamental building blocks of reality could be turned into weapons. It's like discovering that the alphabet itself could be rearranged to create explosions, or that the mathematical constants that govern the universe could be weaponized. The possibility of antimatter weapons has haunted the imagination of both scientists and science fiction writers since the 1930s, when antimatter was first discovered. The physics is straightforward: create antimatter, store it somehow, and then release it to annihilate with ordinary matter. The result would be the most powerful weapon ever conceived, with energy densities that make nuclear weapons look like firecrackers. The military implications were not lost on governments during the Cold War. Both the United States and Soviet Union investigated antimatter weapons, though neither program progressed very far. The technical challenges were, and remain, almost insurmountable. It's like trying to build a sword out of lightning, or a shield out of thunder. The first challenge is production. Creating antimatter requires enormous amounts of energy, far more energy than you get back when it annihilates. It's like trying to run a power plant that consumes more fuel than it produces. Current particle accelerators can create antimatter, but the process is so inefficient that it takes about 10 billion times more energy to create antimatter than you get back from annihilating it. The second challenge is storage. Antimatter must be kept in perfect vacuum, held in place by magnetic fields, and prevented from touching any matter whatsoever. The storage system would need to be incredibly complex, requiring enormous amounts of power, and being vulnerable to any disruption. It's like trying to carry a lit match in a room full of gasoline. One small mistake and everything explodes. The third challenge is delivery. How do you transport antimatter to a target without it annihilating on the way? Any physical container would be made of matter, which would immediately destroy the antimatter. Any delivery system would need to be essentially a mobile particle accelerator, complete with magnetic traps and vacuum systems. But perhaps the most disturbing challenge is the fundamental nature of antimatter weapons. Unlike nuclear weapons, which require specific isotopes and complex engineering, antimatter weapons would be based on the most fundamental symmetries of the universe. Any civilization that develops the technology to create and store antimatter in large quantities would automatically have access to the most powerful weapons possible. This has led some scientists to speculate about what they call the antimatter barrier. The idea that any technologically advanced civilization would eventually discover antimatter, and that the knowledge of how to create it in large quantities would inevitably lead to weapons so powerful they could destroy the civilization that created them. It's a sobering thought. Perhaps the reason we haven't encountered other intelligent civilizations in the universe is that they all eventually discovered antimatter and used it to destroy themselves. The same physics that makes stars shine and planets form also makes it possible to create weapons that could sterilize entire worlds. The military applications aren't limited to simple explosives. Antimatter could theoretically be used to create directed energy weapons, where the gamma rays from annihilation are focused into beams that could destroy targets at great distances. It could be used to create electromagnetic pulse weapons that could disable electronics across entire continents, It could even be used to create weapons that could destroy satellites or space stations by releasing antimatter that would annihilate with the solar wind. But there's a strange comfort in the physics itself. The same properties that make antimatter so dangerous also make it almost impossible to weaponize with current technology. Nature seems to have built in a safety mechanism. Antimatter is so difficult to create and store that it remains beyond the reach of most actors who might want to use it for destructive purposes. The real danger might come not from intentional weapons, but from accidents. As our technology improves, as we learn to create and store larger quantities of antimatter for legitimate scientific purposes, we need to be incredibly careful about safety protocols. The line between a scientific experiment and a potential weapon can be measured in grams. When particles become weapons, they challenge our fundamental assumptions about the relationship between knowledge and power. We're learning to manipulate forces that were present at the creation of the universe, forces that could theoretically be used to destroy it. The question isn't whether we can create antimatter weapons. The question is whether we're wise enough not to. The question haunts urban planners and physicists alike. In a world where we're learning to create and manipulate antimatter, could someone really use it to destroy a city? The answer is both terrifying and strangely comforting. Yes, it's physically possible, but no, it's not practically feasible with current technology. Let's start with the terrifying part. The physics is unambiguous. A relatively small amount of antimatter could indeed destroy a major city. We've calculated that about 2.5 kilograms of antimatter, annihilating with an equal amount of matter, would release the same energy as all the nuclear weapons ever built by humanity. A single kilogram could release energy equivalent to about 20 million tons of TNT, 1,000 times more powerful than the bomb that destroyed Hiroshima. The destruction wouldn't come from blast effects like a conventional explosion. Instead, it would come from an instantaneous burst of gamma radiation traveling at the speed of light. Everyone within several kilometers would receive lethal doses of radiation in the first few seconds. The energy would be so intense, it would literally vaporize everything in the immediate vicinity, turning matter into plasma hot enough to rival the surface of the sun. But here's where the physics becomes strangely reassuring. Creating that much antimatter would require technology and resources that are currently beyond human capability. To produce a kilogram of antimatter, using today's most efficient methods would require more energy than the entire world produces in several years. It would take millions of years to accumulate that much antimatter, and the storage facilities would need to be larger than most cities. The production process itself would be impossible to hide. Creating antimatter requires massive particle accelerators, enormous amounts of electrical power, and highly specialized equipment that would be visible to satellites and intelligence agencies. It's like trying to secretly build a city-sized factory. The infrastructure requirements make concealment nearly impossible. Even if someone could somehow produce large quantities of antimatter, the storage problem remains almost unsolvable. The antimatter would need to be kept in perfect vacuum, held in place by precisely controlled magnetic fields, and prevented from touching any matter whatsoever. The storage facility would need backup power systems, redundant magnetic field generators, and constant monitoring. A single power failure, a tiny vibration, or a microscopic imperfection in the containment system would cause the antimatter to annihilate instantly. The vulnerability of antimatter storage systems makes them almost impossible to use as weapons. Unlike nuclear weapons which remain stable until deliberately detonated, antimatter is constantly trying to destroy itself. It's like trying to use a lit stick of dynamite as a paperweight. The slightest disturbance causes immediate destruction. This inherent instability might actually be antimatter's greatest weakness as a weapon. Any antimatter storage facility would be incredibly vulnerable to attack or sabotage. A single bullet hitting the containment system would cause the antimatter to annihilate, destroying the facility and anyone nearby. It's the ultimate example of a weapon that's more dangerous to its owners than to its intended targets. But the question of whether antimatter could destroy a city forces us to confront a deeper issue. As our technology advances, as we learn to create and store antimatter more efficiently, what safeguards need to be in place? The physics won't change. Antimatter will always be capable of releasing tremendous amounts of energy. The question is whether our wisdom and our safety protocols can keep pace with our technical capabilities. There's also the possibility of accidents. As research facilities create larger quantities of antimatter for legitimate scientific purposes, The potential for catastrophic failures increases. A major malfunction at an antimatter research facility could theoretically cause damage comparable to a nuclear accident, with gamma radiation spreading over a wide area. The psychological impact of antimatter weapons might be even more significant than their physical effects. The knowledge that such weapons are theoretically possible could change the entire calculus of international relations. It's like nuclear weapons, but with even more devastating potential and no radioactive fallout to limit their use. Scientists working with antimatter are acutely aware of these risks. Every safety protocol, every containment system, every backup procedure is designed with the knowledge that even tiny amounts of antimatter can cause tremendous damage. It's a sobering responsibility. Working with substances that could theoretically destroy cities while trying to unlock the secrets of the universe. The question of whether antimatter could destroy a city ultimately becomes a question about the relationship between knowledge and responsibility. We're gaining the power to manipulate the most fundamental forces in the universe, forces that were present at the creation of everything we know. The same physics that explains why stars shine and why we exist also explains how to release more energy than any weapon ever built. Close your eyes and imagine a world exactly like ours but built from antimatter instead of matter. Anti-galaxies spiraling through space, anti-stars burning with anti-light, anti-planets orbiting in perfect antimatter solar systems. This isn't science fiction, it's a serious scientific hypothesis that suggests our universe might be far stranger and more symmetric than we realize. The anti-world hypothesis emerges from a fundamental question. If the laws of physics are perfectly symmetric with respect to matter and antimatter, why shouldn't there be entire regions of space dominated by antimatter? Perhaps the Big Bang didn't create a universe with a slight preference for matter. Perhaps it created a universe with vast regions of matter and equally vast regions of antimatter, separated by empty space. Think about it like cosmic segregation. In the early universe, maybe matter and antimatter didn't mix uniformly. Maybe they formed separate domains, like oil and water refusing to combine. The boundaries between these domains would be incredibly violent places, where matter and antimatter annihilate in brilliant displays of energy. But the interiors of each domain would be perfectly stable, with antimatter galaxies forming and evolving just like the matter galaxies we observe. An antimatter galaxy would look almost identical to a matter galaxy from a distance. Anti-hydrogen atoms would emit the same wavelengths of light as hydrogen atoms. Anti-stars would shine with the same brightness and color as matter stars. Anti-planets would orbit in the same patterns, following the same gravitational law. The only difference would be the charge of every particle, but from billions of light-years away we couldn't detect that difference. This possibility is both thrilling and terrifying. Thrilling, because it suggests that our universe might be far more complex and beautiful than we imagine, with entire civilizations built from antimatter living in regions of space we can't distinguish from matter regions. Terrifying, because it means the universe contains vast quantities of the most dangerous substance we know, spread across distances so large that we can't even comprehend them. The observational evidence for anti-worlds is tantalizing but inconclusive. We do detect gamma rays from certain regions of space that could be the signature of matter-antimatter annihilation at the boundaries between domains. These gamma rays have the right energy and the right distribution to be consistent with cosmic-scale annihilation events, but they could also be explained by other high-energy processes like black hole formation or supernova explosions. The absence of obvious matter-antimatter boundaries in our local region of the universe suggests that if anti-worlds exist, they're far away, perhaps billions of light-years distant. The space between matter and antimatter domains would need to be incredibly empty, with vacuum so perfect that individual particles of matter and antimatter rarely encounter each other. But here's where the hypothesis becomes really intriguing. If anti-worlds exist, they might be completely undetectable by conventional means. We observe the universe through electromagnetic radiation, light, radio waves, X-rays, gamma rays, but antimatter produces exactly the same electromagnetic radiation as matter. An antimatter star would look identical to a matter star in every way we can currently observe. The only way to distinguish between matter and antimatter regions would be to detect the gamma rays produced at the boundaries where they meet. But if those boundaries are billions of light-years away, or if they're separated by regions of space so empty that annihilation events are rare, we might never see direct evidence of anti-worlds. This leads to a profound question. Are we alone in our matter-dominated region of the universe? Are there antimatter versions of Earth, with antimatter life forms built from anti-carbon and anti-water? living under the light of anti-stars. The physics suggests it's possible the same chemical reactions that allow life to exist with matter would work equally well with antimatter. The implications are staggering. If anti-worlds exist, they might contain as much complexity, as much beauty, as much life as our own region of the universe. There might be antimatter civilizations wondering about the nature of reality, antimatter scientists studying the cosmos, antimatter philosophers contemplating the meaning of existence. And they would be forever separated from us by the fundamental incompatibility of matter and antimatter. Any attempt to communicate, any attempt to meet, would result in mutual annihilation. It's like having a mirror image of our entire universe, but one that we can never touch, never visit, never truly know. The anti-world hypothesis reminds us that the universe is under no obligation to be simple or easy to understand. It might be far stranger, far more complex, far more beautiful than we imagine, and perhaps in some distant region of space, anti-beings are looking up at their anti-ski and wondering if they're alone in the universe, never knowing that we're here, wondering the same thing. Have you ever wondered what would happen if your reflection in a mirror suddenly developed a mind of its own? Not just copying your movements, but actively opposing them, fighting back against your very existence. That's essentially what antimatter represents. A perfect reflection of our matter-based reality that would destroy us if we ever truly met. The relationship between matter and antimatter is more complex than simple opposition. They're not just opposites, they're perfect mirrors of each other, with every property matched except for fundamental charge. An antiproton has the same mass as a proton, the same size, the same nuclear properties, but its electric charge is negative instead of positive, and in some deep sense, it's the exact opposite of everything that makes a proton what it is. This mirroring goes beyond simple particle properties. If you could somehow visit an antimatter world, you'd find that the laws of physics work exactly the same way. Water would still freeze at 0 degrees, still boil at 100 degrees. Gravity would still pull things downward, light would still travel at the same speed. Chemistry would follow the same rules, but every atom would be built from antiparticles. Every molecule would be an anti-molecule. The eerie perfection of this mirroring has led some physicists to speculate about what they call mirror symmetry. The idea that the universe might be constructed like a cosmic mirror, with matter on one side and antimatter on the other. Not a physical mirror, but a conceptual one, where every law of physics has an antimatter equivalent. But here's where the mirror analogy becomes unsettling. Unlike a normal mirror, where you can safely coexist with your reflection, matter and antimatter reflections actively destroy each other. It's as if the universe's mirror is made of some cosmic material that causes reflections to fight back, to cancel out their originals in bursts of pure energy. This fighting back isn't malicious or intentional, it's simply the way the universe works. When a particle meets its antiparticle, they don't choose to annihilate, they're compelled to by the fundamental laws of physics. Like two opposing magnetic poles that can't help but attract each other, the annihilation is automatic, instantaneous, and complete. The gamma rays produced by this annihilation carry away all the energy that was stored in the mass of the particles, but they also carry away something more subtle, information. Each annihilation event erases a tiny bit of the universe's complexity, converting organized matter into simple energy. It's like the universe's mirror is not just reflecting reality, but actively simplifying it, removing detail and structure in favor of pure energy. This process has been happening since the first moments after the Big Bang. The cosmic microwave background radiation that fills the universe is largely the afterglow of ancient annihilation events, the ghost of all the antimatter that once existed but was destroyed in the first few minutes of cosmic history. We're literally surrounded by the evidence of this ancient war between matter and antimatter, but the mirror hasn't stopped reflecting. Even today, cosmic rays create brief pairs of matter and antimatter particles in the upper atmosphere. These particles exist for microseconds before finding each other and annihilating, creating tiny flashes of gamma radiation that rain down on us constantly. It's like the universe's mirror is still active, still creating brief glimpses of the antimatter world before destroying them. The strangest part of this cosmic mirror is that it seems to be broken or at least severely damaged. If the universe really is symmetric with respect to matter and antimatter, why do we see so much matter and so little antimatter? It's as if someone took a sledgehammer to the cosmic mirror, leaving mostly one side intact while shattering the other. This broken symmetry is one of the great mysteries of modern physics. Something in the early universe must have caused the mirror to crack, allowing matter to dominate over antimatter. But what could have been powerful enough to break such a fundamental symmetry, and why did it favor matter over antimatter rather than the reverse? The answer might lie in physics we haven't discovered yet, or in subtle asymmetries that we're only beginning to understand. Perhaps the cosmic mirror was never perfect to begin with, always slightly favoring one side over the other. Or perhaps there are hidden dimensions or unknown forces that influence the balance in ways we can't yet detect. Whatever the answer, the fact remains that we live in a universe where reflections fight back, where the fundamental act of looking in a cosmic mirror could result in mutual annihilation. It's a reminder that the universe is far stranger and more dangerous than our everyday experience suggests, and that the very structure of reality might be built on a foundation of cosmic warfare between matter and its perfect deadly reflection. Deep beneath the border between France and Switzerland, scientists are performing the most dangerous dance in human history. They're creating, trapping, and studying antimatter, the universe's most hazardous substance, in quantities that would have seemed impossible just decades ago. Welcome to CERN, where the boundaries between discovery and destruction are measured in individual atoms. The European Organization for Nuclear Research represents humanity's most ambitious attempt to understand the fundamental nature of reality. But it's also home to experiments that would make science fiction writers nervous. Scientists here routinely create temperatures colder than outer space, generate magnetic fields stronger than neutron stars, and produce beams of particles moving at 99.9999% of the speed of light. The antimatter research at CERN is particularly breathtaking in its precision and audacity. In the Alpha experiment, scientists create anti-hydrogen atoms, the antimatter equivalent of the simplest element in the universe. They do this by combining antiprotons with positrons, coaxing them to form antimatter atoms in a process that requires controlling individual particles with extraordinary precision. The creation process itself is like conducting an orchestra where every musician is invisible and any wrong note could cause an explosion. Antiprotons are created by smashing high-energy protons into metal targets, producing showers of particles that must be sorted, filtered, and cooled. The antiprotons emerge moving at about 10% of the speed of light, and must be slowed down to walking speed using complex systems of electric and magnetic fields. Meanwhile, positrons are created by allowing radioactive sodium-22 to decay, producing antimatter electrons that are then guided into the same experimental chamber. The challenge is to get the antiprotons and positrons to combine into antihydrogen atoms without any of them touching the walls of the chamber and annihilating. The magnetic traps used to hold the antihydrogen are marvels of engineering that exist at the very limits of current technology. They create precisely shaped magnetic fields that can hold individual antimatter atoms suspended in perfect vacuum, floating in space like cosmic butterflies caught in invisible nets. The entire system must be kept colder than liquid helium, with temperatures just a few degrees above absolute zero. But here's what makes this dance particularly dangerous. Even tiny amounts of antimatter can cause significant damage if they escape containment. A single microgram of antimatter, an amount so small it would be invisible to the naked eye, contains the same energy as a hand grenade. The experiments at CERN work with even smaller quantities, but the potential for accident is always present. The safety protocols are accordingly extreme. The antimatter is created in quantities of individual atoms, held in traps that automatically shut down if any system fails, and monitored by sensors that can detect problems in microseconds. Multiple backup systems ensure that if anything goes wrong, the antimatter is safely annihilated in controlled conditions rather than escaping into the environment. The irony is that the scientists are trying to study antimatter precisely because it's so dangerous and mysterious. They want to understand whether antimatter obeys the same laws of physics as ordinary matter, whether it falls down or up in a gravitational field, whether it emits light at exactly the same wavelengths as matter. These questions might seem academic, but they could revolutionize our understanding of the universe. The experiments have already produced remarkable results. Scientists have successfully created thousands of antihydrogen atoms, trapped them for minutes at a time, and begun to study their properties. They've measured the spectrum of light emitted by antihydrogen, and found that it's identical to hydrogen, confirming one of the fundamental symmetries of physics. But each experiment is a carefully choreographed dance with destruction. The antihydrogen atoms are created inside the trap, held for as long as possible, and then deliberately released, in controlled conditions where they annihilate against the walls of the chamber. The gamma rays produced by this annihilation are captured and analyzed, providing information about the antimatter that existed for just a few minutes. The ultimate goal is to create enough antihydrogen to perform detailed spectroscopy, to study antimatter gravity, and to test whether antimatter behaves exactly like matter in all respects. If scientists find even tiny differences, it could explain why the universe is dominated by matter rather than antimatter, solving one of the greatest mysteries in physics. But the dance continues to be dangerous. As the experiments become more sophisticated, as scientists learn to create and store larger quantities of antimatter, the potential risks increase. CERN has become a place where the boundaries between discovery and destruction are constantly being tested, where humanity's quest for knowledge brings us face to face with the most dangerous substance in the universe. The scientists there are well aware of the risks. They're not reckless. They are incredibly careful, methodical, and safety conscious, but they're also driven by a profound curiosity about the nature of reality, the desire to understand the universe at its most fundamental level. They're dancing with danger in the service of knowledge, pushing the boundaries of what's possible, while trying to unlock the secrets of existence itself. In the vast cosmic library of the universe, there's a chapter missing from every book, the story of what happens to civilizations that discover how to create antimatter in large quantities. We see evidence of intelligence emerging throughout the cosmos, complex chemistry, organized structures, the building blocks of life. But we don't see evidence of advanced civilizations that have mastered the fundamental forces of nature. Perhaps antimatter is the reason why. The Great Filter hypothesis suggests that there's some evolutionary bottleneck that prevents most life from developing into spacefaring civilizations. It could be the development of complex cells, the emergence of intelligence, the ability to avoid nuclear war, or the challenge of developing sustainable technology. But what if the Great Filter is something more fundamental, the inevitable discovery of how to create and weaponize antimatter? Think about the trajectory of scientific discovery. Every civilization that develops physics will eventually discover antimatter. It's a fundamental consequence of the equations that describe reality. Once you understand quantum mechanics and relativity, antimatter is not just possible, but inevitable. It's written into the very structure of the universe. The problem is that antimatter represents both the ultimate energy source and the ultimate weapon. Any civilization that learns to create it in large quantities automatically gains access to the most powerful technology possible, and the most dangerous. It's like discovering fire, nuclear energy, and the ability to destroy worlds all in the same moment. The physics doesn't leave room for compromise. You can't discover safe antimatter or peaceful antimatter. The same processes that could power interstellar travel could also sterilize entire planets. The same technology that could provide unlimited clean energy could also create weapons that make nuclear bombs look like firecrackers. This creates what we might call the antimatter paradox. Any civilization advanced enough to create antimatter in useful quantities would also be advanced enough to recognize its destructive potential. They would face the same choice we're beginning to face: pursue the technology and risk self-destruction, or avoid it and remain forever limited by conventional energy sources. The mathematics of antimatter weapons are particularly sobering. Unlike nuclear weapons, which require specific isotopes and complex engineering, antimatter weapons would be based on the most fundamental symmetries of physics. Any civilization that develops antimatter technology would automatically understand how to create weapons more powerful than anything we can imagine. The storage and handling challenges might provide some protection, but they're not insurmountable. A sufficiently advanced civilization could potentially solve the containment problems that currently limit antimatter technology. They might develop materials and techniques that make antimatter storage practical, safe, and scalable. But here's the terrifying possibility. Maybe they all do solve these problems, and that's exactly why we don't see them. Maybe the Great Filter isn't the difficulty of creating antimatter technology. Maybe it's the impossibility of controlling it once you have it. Consider the scenario. A civilization develops efficient antimatter production and storage. They begin to use it for energy generation, space travel, and industrial processes. But the same technology that powers their civilization also makes it possible for small groups or even individuals to create weapons capable of destroying entire planets. The more efficient the antimatter technology becomes, the more dangerous it becomes. Unlike nuclear weapons, which require large facilities and international cooperation to produce, antimatter weapons might be scalable down to individual actors. A single person with access to antimatter technology could potentially threaten an entire civilization. The same democratization of energy that makes antimatter appealing also makes it uncontrollable. The result could be a kind of cosmic suicide, where every civilization that reaches the antimatter threshold eventually destroys itself, not through war or environmental destruction, but through the simple impossibility of maintaining stability in a world where individuals can wield the power of stars. This might explain the Fermi paradox, why we don't see evidence of advanced civilizations despite the vast number of planets in the universe. Perhaps intelligence is common, but long-term survival is rare. Perhaps the universe is filled with the remains of civilizations that discovered antimatter and couldn't control it. The implications for our own civilization are profound. We're approaching the antimatter threshold ourselves, developing the technology to create and store larger quantities of this dangerous substance. If the Great Filter hypothesis is correct, we're entering the most dangerous phase of human history, the phase where we gain access to cosmic-scale power without cosmic-scale wisdom. But perhaps there's another possibility. Perhaps some civilizations do survive the antimatter threshold by developing not just the technology to create antimatter, but the wisdom to use it responsibly. Perhaps the Great Filter isn't insurmountable, it's just incredibly difficult to navigate. The question for our species is whether we can be among the survivors. Can we develop antimatter technology while maintaining the social, political, and ethical frameworks necessary to prevent its misuse? Can we gain cosmic power without losing our humanity? The answer might determine not just our future but whether we have any future at all. In the shadow of antimatter's terrifying destructive potential lies a question that could define humanity's future. Can the universe's most dangerous substance also be its most beneficial? The same physics that makes antimatter capable of destroying cities also makes it capable of powering them. The same energy that could end civilization could also take us to the stars. The promise of antimatter begins with its efficiency. Every other energy source we know, burning wood, nuclear fusion, even the theoretical energy of black holes, converts only a fraction of mass into energy. Antimatter annihilation converts 100% of mass into energy, making it the most efficient power source theoretically possible. It's like comparing a candle to the sun, except the difference is even more extreme. A single gram of antimatter annihilating with a gram of ordinary matter would produce enough energy to power a typical American home for about 12,000 years. A kilogram could power a small city for centuries. If we could somehow collect all the antimatter that naturally exists in the observable universe, about the mass of a paperclip, it would provide enough energy to power human civilization for millions of years. The applications seem almost magical. Antimatter could power spacecraft to tremendous speeds, making interstellar travel not just possible, but practical. While chemical rockets can achieve speeds of a few kilometers per second, antimatter rockets could theoretically reach significant fractions of the speed of light. A trip to the nearest star, which would take tens of thousands of years with current technology, could be completed in decades. In medicine, antimatter is already being used to save lives. Positron emission tomography, or PET scans, use the annihilation of positrons to create detailed images of the inside of the human body. The positrons are created by radioactive decay and immediately annihilate with electrons in the patient's tissue, producing gamma rays that can be detected and used to create three-dimensional images of organ function. Scientists are exploring more advanced medical applications. Antimatter beams could potentially be used to destroy cancer cells with extraordinary precision, targeting tumors while leaving healthy tissue undamaged. The gamma rays produced by antimatter annihilation could sterilize medical equipment instantly, or be used to create isotopes for medical imaging and treatment. But perhaps the most intriguing possibility is antimatter's potential to solve the energy crisis. Unlike fossil fuels, which pollute the atmosphere, or nuclear power, which produces radioactive waste, antimatter annihilation produces only energy. The gamma rays it releases can be converted to electricity, and the only byproduct is pure energy. No carbon dioxide, no radioactive waste, no toxic chemicals. The challenge, of course, is production and storage. Creating antimatter currently requires enormous amounts of energy, far more than you get back when it annihilates. It's like trying to run a power plant where you put in 1,000 units of energy to get back 1 unit of energy. The process is so inefficient that antimatter is currently the most expensive substance on Earth, costing trillions of dollars per gram. But technology has a way of improving. The efficiency of antimatter production has increased dramatically over the past few decades, and new techniques are being developed that could potentially make the process more practical. Some scientists speculate that with advanced particle accelerators and superconducting magnetic systems, antimatter production could eventually become energy positive. The storage problem is equally challenging, but potentially solvable. Current magnetic traps can hold antimatter for minutes or hours, but theoretical designs suggest that with superconducting magnets and advanced vacuum systems, antimatter could potentially be stored for years or even decades. Space-based storage systems, where the natural vacuum of space provides perfect isolation, could potentially hold antimatter indefinitely. There's also the possibility of using antimatter catalysis, where small amounts of antimatter are used to trigger fusion reactions in ordinary matter. This could potentially provide the benefits of antimatter energy without requiring large quantities of the dangerous substance. It's like using a match to light a log. You don't need much antimatter to release tremendous amounts of energy from conventional matter. The ethical implications are profound. If antimatter technology could solve the energy crisis, eliminate pollution, and enable interstellar travel, don't we have an obligation to develop it? But if the same technology could enable weapons of unprecedented destruction, don't we have an obligation to avoid it? Perhaps the answer lies not in the technology itself, but in how we approach it. Antimatter research conducted in international cooperation, with rigorous safety protocols and transparent oversight, could potentially harness its benefits while minimizing its risks. The same global cooperation that governs nuclear technology could potentially manage antimatter technology. The question of whether antimatter can be used for good ultimately becomes a question about human nature itself. Are we wise enough to handle cosmic-scale power? Can we develop the technology to create and control antimatter while maintaining the wisdom to use it responsibly? The answer might determine not just our energy future, but our survival as a species. Imagine a rocket engine so efficient that it could accelerate a spacecraft to half the speed of light, making the journey to nearby stars a matter of decades rather than millennia. Imagine fuel so powerful that a single tankful could provide enough energy to power a city for centuries. Now imagine that this same fuel could accidentally destroy the planet if something went wrong. Welcome to the promise and peril of antimatter propulsion. The physics of antimatter rockets is breathtakingly simple and terrifyingly effective. When matter and antimatter annihilate, they convert completely into energy, pure, efficient, and incredibly powerful, unlike chemical rockets, which achieve exhaust velocities of a few kilometers per second. Antimatter rockets could theoretically achieve exhaust velocities approaching the speed of light. It's the difference between throwing a baseball and firing a photon torpedo. The specific impulse, a measure of rocket efficiency of antimatter propulsion, would be about 10 million seconds, compared to about 450 seconds for the best chemical rockets. This means that antimatter rockets could achieve the same velocity changes with about 20,000 times less fuel. A spacecraft that would require thousands of tons of chemical fuel could potentially be powered by grams of antimatter. The implications for space exploration are staggering. With antimatter propulsion, Mars would be reachable in weeks, rather than months, the outer planets in months rather than years, and the nearest stars in decades rather than millennia. It could transform humanity from a single planet species to a genuinely interstellar civilization. But the engineering challenges are equally staggering. The gamma rays produced by antimatter annihilation are incredibly penetrating and incredibly dangerous. Any antimatter rocket would need massive radiation shielding to protect both the spacecraft and its passengers. The reaction chamber would need to withstand temperatures hotter than the core of the sun and radiation levels that would instantly destroy any material we currently know. The fuel handling systems would need to be perfect. Unlike chemical rockets, where a fuel leak might cause a fire or explosion, an antimatter fuel leak would cause complete annihilation. The containment systems would need to be absolutely reliable, with no possibility of failure. It's like trying to build a car where any mechanical problem results in a nuclear explosion. The safety implications extend far beyond the spacecraft itself. An antimatter-powered rocket would essentially be a controlled nuclear explosion with the energy of thousands of atomic bombs. If something went wrong during launch, the results could be catastrophic. The destruction wouldn't be limited to the launch site. The gamma radiation from a major antimatter accident could be lethal across hundreds of kilometers. This has led to proposals for space-based antimatter production and storage facilities, where the dangers would be isolated from populated areas, but even these facilities would pose enormous risks. A major accident at a space-based antimatter facility could potentially damage or destroy satellites, disrupting communications and navigation systems across the entire planet. The quantities of antimatter required for interstellar travel make the safety challenges even more daunting. A spacecraft traveling to nearby stars would need kilograms of antimatter, amounts that would require centuries to produce. With current technology, would contain enough energy to destroy entire cities if accidentally released. Yet the potential benefits are so enormous that research continues. NASA and other space agencies have funded studies of antimatter propulsion, exploring theoretical designs and conducting small-scale experiments. Some designs propose using antimatter to trigger fusion reactions in ordinary matter, potentially providing the benefits of antimatter propulsion without requiring large quantities of the dangerous substance. The timeline for practical antimatter propulsion remains highly uncertain. Current antimatter production methods are phenomenally expensive and inefficient. Creating enough antimatter to power a spacecraft would cost trillions of dollars and require more energy than the entire world produces. But technology has a way of improving, and breakthroughs in particle physics could potentially make antimatter production more practical. The question isn't just whether we can build antimatter rockets, but whether we should. The same technology that could take us to the stars could also be used to create weapons of unprecedented destruction. The same fuel that could power interstellar exploration could also be used to destroy the civilization that created it. Perhaps the answer lies in the timing. If we develop antimatter propulsion before we develop the wisdom to use it responsibly, it could indeed be our final mistake. But if we approach the technology with appropriate caution, international cooperation and rigorous safety protocols, it could be the key to humanity's expansion into the cosmos. The choice between rocket fuel of the future and final mistake might not be determined by the technology itself, but by the wisdom and maturity of the civilization that develops it. Are we ready for cosmic-scale power? Can we handle the responsibility that comes with the ability to travel between stars? The answer might determine not just our future in space, but our future as a species. Picture this. You're sitting in your backyard on a summer evening, watching the International Space Station drift across the sky like a slow-moving star. It's traveling at about 1,700 miles per hour, which sounds incredibly fast until you realize it would take that station over 73,000 years to reach our nearest stellar neighbor, Proxima Centauri. That's a lot of packed lunches. But what if I told you there's a substance so powerful that just a few grams could propel a spacecraft to nearby stars in mere decades? Welcome to the world of antimatter propulsion, where science fiction bumps into the beautiful, terrifying reality of physics. Think of antimatter as the universe's most efficient fuel. When matter and antimatter meet, they don't just burn, they completely annihilate each other, converting 100% of their mass into pure energy. Einstein's famous equation, E=mc², tells us that even a tiny amount of mass contains enormous energy. But with antimatter, we're not just tapping into that energy, we're releasing all of it. To put this in perspective, imagine your car's gas tank. A gallon of gasoline contains about 31 million joules of energy. Now, if you could somehow convert just 1 gram of matter, about the weight of a paperclip, completely to energy, you'd get 90 trillion joules. That's enough energy to power your house for about 2,500 years. It's like having a paperclip that contains the energy of 3 million gallons of gasoline. The concept is beautifully simple. In an antimatter rocket, you'd store antimatter in magnetic bottles because antimatter can't touch normal matter without annihilating. Then carefully allow it to meet regular matter in a controlled reaction chamber. The resulting energy would be directed out the back of the spacecraft, propelling it forward at incredible speeds. But here's where the poetry of physics meets the harsh reality of engineering. Creating antimatter is like trying to capture lightning in a bottle while riding a unicycle. Currently, our most advanced particle accelerators can produce only about 10 billionths of a gram of antimatter per year. The entire world's antimatter production wouldn't be enough to power a light bulb for more than a few minutes. And the cost, producing a single gram of antimatter would cost about $25 trillion more than the entire global economy produces in a year. It's like trying to buy a cup of coffee with the gross domestic product of Earth. Yet scientists and engineers continue to dream. NASA and other space agencies have seriously studied antimatter propulsion concepts. The idea is tantalizing. A spacecraft powered by antimatter could accelerate continuously, reaching perhaps 10% the speed of light. Alpha Centauri, which would take conventional rockets tens of thousands of years to reach, might be accessible in just 40 years. The engineering challenges are like something from a particularly ambitious science fiction novel. How do you store something that destroys anything it touches? How do you contain a substance that makes nitroglycerin look like a gentle spring breeze? Magnetic confinement systems would need to be absolutely perfect. One tiny failure, and your fuel supply would detonate with the force of thousands of nuclear bombs. But perhaps the most beautiful aspect of antimatter propulsion is what it represents. Humanity's eternal desire to reach beyond our current limitations. We've always been creatures who looked at the horizon and wondered what lay beyond it. First we crossed oceans, then we took to the skies. Then we reached for the moon. Now we're contemplating using the fundamental forces of the universe itself as our engine. There's something deeply moving about the idea that the same physics that created the cosmos, the dance between matter and antimatter in the first moments after the Big Bang, might one day carry us to the stars. It's as if the universe has provided us with the ultimate key to its own vast distances, wrapped in the most dangerous and beautiful package imaginable. For now, antimatter rockets remain in the realm of theoretical physics and engineering dreams. But every impossibility was once just that. Impossible, until someone figured out how to make it work. The Wright brothers' first flight lasted just 12 seconds. 66 years later, we walked on the moon. Maybe someday, when you're watching that space station drift across the evening sky, you'll remember that we once thought reaching the stars was impossible too. And maybe, just maybe, you'll see another light up there. One that's carrying human beings to distant suns, powered by the most dangerous and wondrous substance in the universe. Picture this. You're sitting in your backyard on a summer evening, watching the International Space Station drift across the sky like a slow-moving star. It's traveling at about 17,500 miles per hour, which sounds incredibly fast until you realize it would take that station over 73,000 years to reach our nearest stellar neighbor, Proxima Centauri. That's a lot of packed lunches. But what if I told you there's a substance so powerful that just a few grams could propel a spacecraft to nearby stars in mere decades? Welcome to the world of antimatter propulsion, where science fiction bumps into the beautiful, terrifying reality of physics. Think of antimatter as the universe's most efficient fuel. When matter and antimatter meet, they don't just burn, they completely annihilate each other, converting 100% of their mass into pure energy. Einstein's famous equation, E=mc², tells us that even a tiny amount of mass contains enormous energy. But with antimatter, we're not just tapping into that energy, we're releasing all of it. To put this in perspective, imagine your car's gas tank. A gallon of gasoline contains about 31 million joules of energy. Now, if you could somehow convert just 1 gram of matter, about the weight of a paperclip, completely to energy, you'd get 90 trillion joules. That's enough energy to power your house for about 2,500 years. It's like having a paperclip that contains the energy of 3 million gallons of gasoline. The concept is beautifully simple. In an antimatter rocket, you'd store antimatter in magnetic bottles, because antimatter can't touch normal matter without annihilating, then carefully allow it to meet regular matter in a controlled reaction chamber. The resulting energy would be directed out the back of the spacecraft, propelling it forward at incredible speeds. But here's where the poetry of physics meets the harsh reality of engineering. Creating antimatter is like trying to capture lightning in a bottle while riding a unicycle. Currently, our most advanced particle accelerators can produce only about 10 billionths of a gram of antimatter per year. The entire world's antimatter production wouldn't be enough to power a light bulb for more than a few minutes. And the cost? Producing a single gram of antimatter would cost about $25 trillion more than the entire global economy produces in a year. It's like trying to buy a cup of coffee with the gross domestic product of Earth. Yet scientists and engineers continue to dream. NASA and other space agencies have seriously studied antimatter propulsion concepts. The idea is tantalizing. A spacecraft powered by antimatter could accelerate continuously, reaching perhaps 10% the speed of light. Alpha Centauri, which would take conventional rockets tens of thousands of years to reach, might be accessible in just 40 years. The engineering challenges are like something from a particularly ambitious science fiction novel. How do you store something that destroys anything it touches? How do you contain a substance that makes nitroglycerin look like a gentle spring breeze? Magnetic confinement systems would need to be absolutely perfect. One tiny failure, and your fuel supply would detonate with the force of thousands of nuclear bombs. But perhaps the most beautiful aspect of antimatter propulsion is what it represents: humanity's eternal desire to reach beyond our current limitations. We've always been creatures who looked at the horizon and wondered what lay beyond it. First we crossed oceans, then we took to the skies, then we reached for the moon. Now we're contemplating using the fundamental forces of the universe itself as our engine. There's something deeply moving about the idea that the same physics that created the cosmos, the dance between matter and antimatter in the first moments after the Big Bang, might one day carry us to the stars. It's as if the universe has provided us with the ultimate key to its own vast distances, wrapped in the most dangerous and beautiful package imaginable. For now, antimatter rockets remain in the realm of theoretical physics and engineering dreams, but every impossibility was once just that: impossible, until someone figured out how to make it work. The Wright brothers' first flight lasted just 12 seconds. 66 years later, we walked on the moon. Maybe someday, when you're watching that space station drift across the evening sky, you'll remember that we once thought reaching the stars was impossible too. And maybe, just maybe, you'll see another light up there, one that's carrying human beings to distant suns, powered by the most dangerous and wondrous substance in the universe. Sometimes the most profound questions come from the simplest observation, like when you're lying on your back in a meadow, watching clouds drift across the sky, and you suddenly wonder, why is the sky so empty? Between the stars, between the galaxies, there's all this space, but what's actually in it? It turns out this question leads us to one of the most mysterious relationships in physics: the possible connection between antimatter and dark energy, the invisible force that's tearing the universe apart. Let's start with what we know, or think we know. About 95% of the universe is made of things we can't see or touch. About 27% is dark matter, mysterious stuff that doesn't emit light, but has gravitational effects we can measure. The remaining 68% is even stranger: dark energy, a force that seems to be pushing space itself apart, causing the universe to expand at an accelerating rate. Picture the universe as a balloon being inflated. For the first several billion years after the Big Bang, gravity was winning. The expansion was slowing down as matter pulled back on itself. But then about 5 billion years ago something changed. The expansion started speeding up again, as if someone had connected a more powerful pump to our cosmic balloon. This acceleration was so unexpected that when astronomers first discovered it in 1998, they checked their calculations multiple times. It was like dropping a ball and watching it fall upward. The force causing this acceleration, dark energy, remains one of the deepest mysteries in science. But here's where antimatter enters the picture, like a character in a mystery novel who might hold the key to everything. Some physicists have wondered, could there be a connection between the universe's missing antimatter and its mysterious dark energy? Think about it this way: if matter and antimatter are truly symmetric, perfect opposites, then perhaps they don't just have opposite charges and spins. Maybe they have opposite gravitational effects too. While regular matter pulls things together through gravity, antimatter might push them apart. If this were true, then antimatter wouldn't just be matter's opposite, it would be gravity's opposite. This idea is both elegant and radical. It suggests that the universe's expansion isn't driven by some mysterious new force, but by the same antimatter that should have been created in equal amounts during the Big Bang. Instead of being destroyed, perhaps most of the antimatter was somehow separated from regular matter, and now exists in vast invisible reservoirs, pushing the universe apart through anti-gravity. The mathematics of this possibility are tantalizing. If you calculate how much antimatter would be needed to drive the observed cosmic acceleration, you get numbers that are remarkably close to the amount of antimatter that went missing after the Big Bang. It's like finding that the exact amount of money missing from your bank account equals the cost of that mysterious charge on your credit card. But the universe, as always, is more complicated than our elegant theories. Direct tests of antimatter's gravitational behavior are incredibly difficult. We've only recently begun experiments to measure whether antimatter falls up or down in Earth's gravitational field. The technical challenges are enormous. Imagine trying to weigh a soap bubble in a hurricane while wearing oven mitts. Yet the implications are staggering. If antimatter does have repulsive gravitational effects, It would revolutionize our understanding of gravity itself. Einstein's general relativity, which has passed every test for over a century, assumes that all forms of energy and matter curve spacetime in the same way. Antimatter with anti-gravity would require new physics, new equations, new ways of thinking about the fabric of reality. There's something poetic about this possibility. It suggests that the universe isn't just expanding, it's being torn apart by its own missing half. Every galaxy, every star, every atom of matter in the universe is connected to its absent antimatter twin through the very geometry of space and time. Consider the implications for cosmic history. If antimatter creates anti-gravity, then the early universe must have been a battleground between matter's pull and antimatter's push. The formation of the first stars and galaxies would have been shaped by this cosmic tug-of-war. The large-scale structure of the universe, the web of galaxies separated by vast voids, might reflect the ancient scars of this battle. Some physicists have proposed even more exotic possibilities. What if antimatter doesn't just create anti-gravity? What if it actually exists in regions of space where time flows backward? This would make antimatter not just matter's opposite, but time's opposite too. The expanding universe might be accompanied by contracting regions of antimatter, creating a cosmic symmetry that's hidden from our direct observation. These ideas remain highly speculative, existing at the boundary between established physics and pure imagination, but they remind us that the universe is under no obligation to make sense according to our current understanding. Dark energy was completely unexpected. The missing antimatter remains unexplained. The connection between them might be the key to understanding both mysteries. As you look up at the night sky, remember that you're seeing only a tiny fraction of what's really there. The darkness between the stars might not be empty at all. It might be filled with the ghostly presence of antimatter, pushing the universe apart with invisible hands, writing the future of cosmos in a language we're only beginning to learn to read. The most dangerous substance in the universe might also be the force that determines the universe's ultimate fate, and that perhaps is the most beautiful irony of all. There's a moment just before you fall asleep, when time seems to do something strange. The day's events don't flow in their usual forward march. Instead, they seem to swirl and eddy, mixing past and future in ways that feel both impossible and perfectly natural. It's in moments like these that we might glimpse something profound about the nature of time itself and its mysterious relationship with antimatter. The question of whether antimatter flows backward in time isn't just a curiosity from the pages of science fiction, it's a genuine puzzle that has occupied some of the brightest minds in physics for decades. And the answer, like so many answers in quantum mechanics, is both simpler and more strange than we might expect. Let's start with something you can picture, a movie playing in reverse. Water flows upward, broken glasses reassemble themselves, people walk backward while speaking in reverse. It looks wrong, because it violates our deep intuition about the direction of time. But here's the thing, most of the fundamental laws of physics don't actually care which direction time flows. They work just as well backward as forward. This symmetry is called time reversal invariance, and it's one of the most elegant principles in physics. Newton's laws, Maxwell's equations for electromagnetism, even Einstein's relativity, they all treat time as a dimension that could in principle flow either way. It's only when large numbers of particles get involved that we see time's arrow clearly pointing in one direction. But antimatter adds a fascinating twist to this story. In the 1940s, physicist Richard Feynman proposed something remarkable, that antimatter particles might actually be regular particles moving backward through time. It's an idea that sounds like pure fantasy until you realize how beautifully it solves certain puzzles in quantum mechanics. Imagine watching the annihilation of an electron and a positron. In our normal view, two particles approach each other, collide, and disappear in a flash of energy. But Feynman suggested another way to think about it. What if there's really only one particle, an electron that's bouncing back and forth through time? When it travels forward through time, we see it as an electron. When it travels backward through time, we see it as a positron. This isn't just mathematical poetry, it's a perspective that makes certain calculations in quantum field theory much simpler. It's as if the universe has a built-in economy of motion, using the same particle to play multiple roles in the cosmic drama, simply by having it travel in different temporal directions. The implications are mind-bending. If antimatter really does flow backward through time, then every antimatter particle in the universe might be a messenger from the future, carrying information about events that haven't happened yet from our perspective. The positron, was created when cosmic rays hit our atmosphere, might have lived its entire existence in reverse, beginning at the moment of its annihilation and ending at the moment of its creation. But time reversal in quantum mechanics is more subtle than simple backward motion. It's more like the universe playing a cosmic game of improvisation, where cause and effect become so intertwined that they lose their usual meaning. In the quantum world, events don't just happen. They exist in superposition, simultaneously occurring and not occurring until observation collapses them into definite states. This quantum perspective on time helps explain one of antimatter's most puzzling properties: its perfect symmetry with regular matter. If antimatter particles are indeed regular particles moving backward through time, then their opposite charges and spins aren't really opposites at all. They're the same properties viewed from a different temporal perspective. Consider the implications for our understanding of causality. In our everyday experience, causes precede effects. You drop a glass, then it breaks. But in the quantum realm, with particles potentially moving backward through time, this sequence becomes more like a dance where partners sometimes lead and sometimes follow, where the music of causality plays in rhythms we can barely perceive. Some physicists have proposed that this time-reverse symmetry might explain the universe's apparent preference for matter over antimatter. If antimatter truly flows backward through time, then the Big Bang, which created equal amounts of matter and antimatter, might have been both a beginning and an end. The antimatter created at the Big Bang might have flowed backward to earlier times, while the matter flowed forward to later times, creating the apparent asymmetry we observe today. This idea transforms our understanding of cosmic history. Instead of thinking about the Big Bang as a single moment of creation, we might need to think about it as a temporal intersection, a place where forward-flowing matter and backward-flowing antimatter briefly coexisted before diverging into separate temporal streams. The experimental evidence for time-reversed antimatter remains subtle and indirect. We can't directly observe particles moving backward through time. By definition, such observations would appear to us as normal particles moving forward. But certain symmetries in particle physics, particularly in the behavior of exotic particles called kaons, hint at deep connections between time reversal and antimatter. As you drift off to sleep tonight, remember that time itself might be more fluid than our waking minds can grasp. The antimatter that once filled the universe might not have been destroyed. It might have simply flowed backward to earlier times, creating a kind of temporal symmetry that makes the cosmos whole. Perhaps the most dangerous substance in the universe is dangerous precisely because it challenges our most basic assumptions about the nature of time itself. And maybe, in those moments just before sleep, when time seems to flow in strange directions, we're glimpsing something true about the deeper structure of reality. A structure where past and future dance together in ways that defy our ordinary understanding, but reveal the universe's profound and beautiful symmetry. Sometimes the most powerful medicines come from the most unexpected places. Aspirin from willow bark, penicillin from mold, and now, some of the most precise medical imaging and promising cancer treatments come from antimatter. That same substance that could theoretically destroy cities is quietly saving lives in hospitals around the world. It's a beautiful irony that deserves a moment of reflection. The annihilation of matter and antimatter, which represents the most violent reaction possible in physics, has become one of the gentlest tools in modern medicine. It's like discovering that lightning, properly harnessed, can power a nightlight for a premature baby's incubator. Let's start with something you might have experienced: a PET scan. PET stands for positron emission tomography. And yes, those positrons are antimatter particles. When you receive a PET scan, you're given a small amount of radioactive glucose that's been tagged with a positron-emitting isotope. This special glucose travels through your bloodstream and concentrates in areas of high metabolic activity, like tumors, which consume glucose voraciously. Here's where the antimatter magic happens. When the positrons from the radioactive glucose encounter electrons in your body, they annihilate each other, producing two gamma rays that fly off in exactly opposite directions. The PET scanner detects these gamma rays and, using sophisticated mathematics, reconstructs a three-dimensional image of where the annihilations occurred. It's like having a conversation with your body, using the language of annihilation. The antimatter particles serve as messengers, carrying information about your body's internal processes and translating them into images that doctors can read. The most violent reaction in physics becomes a gentle whisper that reveals hidden tumors, monitors brain activity, or tracks the effectiveness of treatments. The precision is extraordinary because the two gamma rays travel in opposite directions. The scanner can determine exactly where each annihilation occurred. It's like triangulating the location of a firecracker by listening to the echo from two different positions, except the firecracker is the controlled annihilation of matter and antimatter, and the echo is pure energy traveling at the speed of light. But PET scans are just the beginning. Researchers are exploring even more direct ways to use antimatter in medicine. One promising approach is called antimatter therapy, where beams of antiprotons are used to treat cancer with unprecedented precision. Traditional radiation therapy is like trying to paint a detailed picture with a very broad brush. The radiation damages cancer cells, but it also damages healthy tissue along the way. Antimatter therapy, by contrast, is like having a brush that's only one atom wide and can paint exactly where you want it to. Here's how it works. Antiprotons can be slowed down and precisely targeted to specific locations in the body. As they travel through healthy tissue, they cause minimal damage, but when they reach their target, a tumor for example, they annihilate with protons in the cancer cells, releasing their energy exactly where it's needed most. It's like having a guided missile that only explodes when it reaches its intended destination. The energy release from antimatter annihilation is not just powerful, it's also perfectly localized. Unlike conventional radiation which spreads out as it travels, antimatter delivers its energy in a focused burst at the point of annihilation. This means doctors could potentially destroy cancer cells with extraordinary precision, while leaving surrounding healthy tissue completely untouched. The challenges, of course, are enormous. Producing enough antimatter for medical use is incredibly expensive and technically complex. Storing and transporting antimatter requires magnetic containment systems that make the technology in science fiction movies look simple. And controlling the annihilation process with medical precision requires engineering that pushes the boundaries of what's currently possible. But the potential benefits are equally extraordinary. Imagine treating a brain tumor without affecting the healthy brain tissue around it. Think about destroying cancer cells deep within the body without any of the side effects of conventional chemotherapy or radiation. Consider the possibility of medical treatments that work at the cellular level with the precision of a watchmaker. Some researchers are exploring even more exotic possibilities. What if antimatter could be used not just to destroy diseased cells but to repair healthy ones? The energy released from controlled annihilation might be harnessed to power cellular repair mechanisms, essentially using the universe's most violent reaction to heal rather than harm. There's something deeply moving about this application of antimatter. The same physics that created the universe in the Big Bang, that powers the most energetic events in the cosmos, is being channeled into healing human bodies. It's a reminder that the forces that govern stars and galaxies also operate within us, and that understanding the universe's most extreme phenomena can lead to the most intimate kinds of healing. As you think about the antimatter quietly at work in medical facilities around the world, remember that science often finds its most profound applications in the most unexpected places. The substance that could theoretically end civilization is instead helping to preserve and heal life one precise annihilation at a time. It's a beautiful example of how human ingenuity can transform even the most dangerous forces into instruments of healing. And maybe, in that transformation we see something hopeful about our species. Our ability to take the universe's most violent reactions and turn them into gentle tools of compassion and care. Picture this: you're standing at the edge of a waterfall, watching water cascade over the rocks and disappear into the mist below. There's something mesmerizing about that boundary, the place where the familiar becomes unknown, where matter transforms into something else entirely. Black holes are like cosmic waterfalls, except instead of water disappearing into mist, it's matter and energy disappearing into, well, that's where antimatter might hold some fascinating clues. Black holes have always been nature's ultimate magic trick. The regions where gravity becomes so strong that not even light can escape. Cosmic points of no return, where the familiar rules of physics start to break down. But in the 1970s, physicist Stephen Hawking discovered something extraordinary. Black holes aren't completely black. They actually emit radiation, and this radiation might be intimately connected to the universe's missing antimatter. Let's start with the beautiful strangeness of Hawking radiation. Remember those quantum fluctuations we talked about earlier, the constant creation and annihilation of particle pairs that happens throughout empty space. Near a black hole, these fluctuations take on a dramatic new character. Imagine a pair of virtual particles, one matter one antimatter, spontaneously appearing right at the edge of a black hole's event horizon. Normally, these particles would quickly annihilate each other and disappear, but the black hole's immense gravity creates a cosmic game of chance. Sometimes one particle falls into the black hole, while its partner escapes into space. Here's where it gets beautifully weird. The particle that escapes becomes real, no longer virtual. It carries away energy from the black hole, causing the black hole to slowly evaporate. It's as if the black hole is paying for the escaped particle's existence by giving up some of its own mass and energy. But which particle escapes, the matter or the antimatter? This question leads us into some of the deepest mysteries in physics. If black holes preferentially absorb matter particles while allowing antimatter particles to escape, they could serve as cosmic antimatter factories, slowly converting their mass into antimatter radiation over trillions of years. This process is almost impossibly slow. A black hole, with the mass of our Sun, would take longer than the current age of the universe to lose even a tiny fraction of its mass to Hawking radiation. But stellar mass black holes are actually gaining mass faster than they lose it, feeding on cosmic dust and gas. The black holes that are actually evaporating are the microscopic ones, primordial black holes that might have formed in the early universe. These tiny black holes, if they exist, would be finishing their evaporation right about now, ending their existence in brilliant flashes of gamma rays. And here's the fascinating part. The final moments of a black hole's evaporation might produce significant amounts of antimatter. Each dying black hole could be like a cosmic antimatter bomb, scattered throughout the universe. Some physicists have proposed that this process might help explain the universe's apparent antimatter deficit. If the early universe was filled with tiny black holes, and if these black holes preferentially produced antimatter as they evaporated, then the missing antimatter might not be missing at all. It might be locked away in the final death throes of primordial black holes. The connection between black holes and antimatter runs even deeper. Black holes are described by some of the most symmetric equations in physics. They don't care whether they're made of matter or antimatter. A black hole formed from antimatter would be indistinguishable from one formed from regular matter. This suggests that somewhere in the universe there might be antimatter black holes, cosmic voids that formed from the collapse of antimatter stars. But the most mind-bending possibility involves the information paradox, one of the deepest puzzles in modern physics. When matter falls into a black hole, what happens to the information it carries? Quantum mechanics says information can never be truly destroyed, but general relativity suggests it disappears forever behind the event horizon. Some physicists have proposed that antimatter might be the key to resolving this paradox. If black holes convert matter to antimatter as they evaporate, then the information carried by the original matter might be preserved in the antimatter radiation. It's as if the black hole is not destroying information but translating it, converting matter's story into antimatter's mirror image. This idea transforms black holes from cosmic destroyers into cosmic translators. Instead of erasing information from the universe, they might be converting it from one form to another, preserving the universe's memory in a language written in antimatter. The implications stretch far beyond black holes themselves. If this connection is real, and every black hole in the universe is slowly converting matter into antimatter, creating a cosmic cycle where the universe's missing antimatter is gradually being restored. The process is incredibly slow. It would take longer than the current age of the universe for significant amounts of antimatter to be produced this way. But it suggests that the universe has its own built-in mechanism for maintaining balance. As you look up at the night sky, remember that it's peppered with these cosmic translators, black holes quietly converting matter to antimatter, preserving information in forms we barely imagine, maintaining the universe's deepest symmetries through processes that span cosmological time. The most dangerous substance in the universe might be intimately connected to the most mysterious objects in the cosmos. And in that connection, we might find answers to some of the deepest questions about reality itself. Questions about information, time, and the fundamental nature of existence. Sometimes the most profound questions start with the simplest words. What if? What if you had turned left instead of right at that intersection? What if you had taken that other job? What if the universe had unfolded differently in its first moments? Tonight, let's explore one of the most fascinating what-if scenarios in cosmology. What if antimatter had won the cosmic battle in the early universe? To understand this possibility, we need to travel back to the very beginning, not just to the Big Bang, but to the first trillionth of a second afterward, when the universe was smaller than an atom and hotter than the core of any star. In those first moments, matter and antimatter existed in perfect balance, constantly creating and annihilating each other in a cosmic dance of creation and destruction. But something broke that perfect symmetry. For every billion antimatter particles, there were 1,000,000,001 matter particles. When the annihilation was complete, only that tiny excess of matter remained, the matter that eventually became stars, planets, and us. But what if the numbers had been reversed? What if for every billion matter particles, there had been 1,000,000,001 antimatter particles? The answer is both simple and profound. We would live in an antimatter universe, and we would never know the difference. This is one of the most beautiful aspects of antimatter physics. The laws of physics are almost perfectly symmetric between matter and antimatter. An antimatter universe would evolve in essentially the same way as our matter universe. Antimatter stars would shine with the same colors. Antimatter planets would orbit in the same patterns. And antimatter life, if it evolved, would follow the same biological principles. Think about it. An antimatter sun would fuse antimatter hydrogen into antimatter helium, releasing energy that would warm an antimatter Earth. Antimatter water would flow in antimatter rivers. Antimatter plants would photosynthesize antimatter carbon dioxide, and antimatter humans would wonder about the nature of their antimatter universe. The symmetry is so perfect that antimatter beings would call their substance matter and our substance antimatter. They would consider themselves normal and us exotic. From their perspective, we would be the dangerous ones, the strange entities made of annihilating particles that could destroy their world with a touch. But an antimatter-dominated universe would differ from ours in subtle ways. Some of the tiny asymmetries we observe in particle physics, the slight preferences for certain decay modes in exotic particles, would be reversed. The cosmic microwave background radiation would carry slightly different patterns. The formation of the first stars and galaxies might have proceeded with tiny differences in timing and structure. These differences would be like variations in a cosmic symphony. The same melody played in a different key with slightly different harmonies and rhythms. The overall structure would be familiar, but the details would tell a different story. One of the most intriguing possibilities involves the role of magnetic fields. In our universe, magnetic fields are created by moving electric charges. In an antimatter universe, the charges would be reversed, creating magnetic fields that point in opposite directions. This could affect everything from the behavior of cosmic rays to the formation of planetary magnetospheres. An antimatter Earth might have a magnetic field that points south instead of north. Aurora would still dance in the polar skies, but they might display different colors or patterns. Compasses would point in the opposite direction, and the Van Allen radiation belts would trap different types of particles. The chemistry of an antimatter universe would be fascinating to consider. Antimatter atoms would have the same electron shells and bonding properties as regular atoms, so antimatter chemistry would follow the same rules. But the nuclear physics would be subtly different. Antimatter nuclei would have different magnetic moments, potentially affecting certain types of chemical reactions and molecular structures. Perhaps most intriguingly, an antimatter universe might have evolved different solutions to the same physical challenges. If life evolved in such a universe, it might have developed different biochemical pathways, different molecular structures, different approaches to storing and processing information. The building blocks would be antimatter, but the resulting structures could be wonderfully alien. The communication between matter and antimatter civilizations would be the ultimate challenge. Any physical contact would result in annihilation, so information would have to be exchanged through radiation, photons that are their own antiparticles, and can travel safely between matter and antimatter realms. Imagine trying to establish communication with an antimatter civilization. You couldn't send physical objects or even atoms. Instead, you would need to encode information in patterns of light, magnetic fields, or gravitational waves. The first message might be as simple as prime numbers encoded in radio pulses, but the implications would be staggering. Proof that intelligence can arise from either form of matter. The cosmic implications of an antimatter-dominated universe extend far beyond individual planets or star systems. The large-scale structure of the universe, the cosmic web of galaxies separated by vast voids, might have evolved differently. Dark matter, which makes up most of the universe's mass, might interact differently with antimatter than with regular matter, potentially creating different patterns of galaxy formation and evolution. Some physicists have speculated that our universe might actually contain large regions dominated by antimatter, separated from our matter-dominated region by vast boundaries where annihilation creates walls of energy. These boundaries would be invisible to us, sheets of gamma radiation marking the borders between matter and antimatter domains. If such regions exist, they would be like parallel universes existing in the same space as ours but forever separated by the lethal barrier of annihilation. Antimatter galaxies might be shining in distant parts of the universe, their light indistinguishable from our own galaxy's light, their civilizations wondering if they are alone in the cosmos. The thought experiment of an antimatter-dominated universe also raises profound questions about the nature of existence itself. If antimatter beings in an antimatter universe would be essentially identical to us in every way that matters, what does that tell us about the fundamental nature of reality? Are we simply one possible configuration of energy and information, with antimatter representing an equally valid alternative? Perhaps the most beautiful aspect of this cosmic what-if is what it reveals about the universe's underlying unity. Matter and antimatter are not truly opposites. They are complementary aspects of a deeper symmetry. In imagining an antimatter universe, we glimpse the possibility that existence itself transcends the particular forms it takes. As you drift off to sleep tonight, remember that somewhere in the vast cosmos, there might be antimatter beings looking up at their antimatter stars, wondering about the nature of their universe, dreaming dreams that are the mirror image of our own. And in that possibility, we find not alienation but connection, proof that consciousness and wonder are not accidents of matter or antimatter, but fundamental features of the cosmos itself. There's something both melancholy and beautiful about endings. The last day of summer, the final page of a beloved book, the moment when a song fades into silence. Tonight, as we conclude our journey through the strange and wonderful world of antimatter, let's contemplate what this most dangerous substance might tell us about the ultimate ending, the fate of the universe itself. The universe is writing its own story, and antimatter holds some of the most important clues about how that story might end. To understand these clues, we need to think about timescales that dwarf human experience. Not just millions or billions of years, but trillions upon trillions of years into the future, when the stars have burned out and the cosmos has grown cold and dark. In the far future, when the last stars have exhausted their nuclear fuel and collapsed into white dwarfs, neutron stars or black holes, the universe will enter what cosmologists call the degenerate era. It will be a time when the only sources of energy are the slow radioactive decay of protons and the even slower evaporation of black holes through Hawking radiation. And here's where antimatter becomes crucial to the story. If protons, the fundamental building blocks of atomic nuclei, eventually decay, they might decay into lighter particles, including positrons. This means that in the far future, the universe might be slowly filling with antimatter as regular matter breaks down. Imagine the cosmic irony. The same antimatter that was nearly eliminated in the universe's first moments might make a grand return in its final chapters. The universe that began with matter's victory over antimatter might end with antimatter's slow but steady comeback. The timescales involved are almost incomprehensible. Proton decay, if it occurs at all, happens so slowly that a single proton has only a tiny chance of decaying during the entire current age of the universe. But given enough time, perhaps 10 or 36 years, even the most stable matter would eventually succumb to this ultimate form of radioactive decay. As this process unfolds over cosmic eons, the universe would gradually fill with the products of proton decay: positrons, neutrinos, and photons. The positrons, antimatter, electrons, would occasionally encounter the few remaining electrons, annihilating in brief flashes of gamma rays. These rare annihilations might be the only events breaking the cosmic silence of the far future. But the story doesn't end there. Black holes, those cosmic graveyards where matter goes to disappear, might have the final word. Through Hawking radiation, black holes slowly evaporate, and the particles they emit might include significant amounts of antimatter. As we discussed earlier, the final moments of a black hole's existence could produce a burst of antimatter particles, each one carrying away the last memories of the matter that once fell beyond the event horizon. This suggests a beautiful symmetry in the universe's life cycle. The cosmos began with equal amounts of matter and antimatter, saw matter win a narrow victory, and might end with antimatter slowly reclaiming its place as the dominant form of particles in the universe. It's as if the universe is playing out a cosmic drama, where the seemingly defeated protagonist makes a triumphant return in the final act. The implications extend beyond mere particle physics. If antimatter has different gravitational properties than regular matter, if it creates repulsive rather than attractive gravitational effects, then the far future universe might be dominated by anti-gravity. This could dramatically affect the universe's expansion, potentially accelerating it even further, or creating complex patterns of cosmic evolution that we can barely imagine. Some physicists have proposed even more exotic scenarios. What if the universe's expansion eventually reverses, causing space itself to contract in a big crunch? In such a scenario, the antimatter created during the universe's long decline might play a crucial role in the final compression, potentially creating conditions where matter and antimatter are reunited in a final cosmic annihilation. Or perhaps the universe will expand forever, growing ever colder and more dilute, until only isolated particles remain, separated by vast distances. In this heat-death scenario, the occasional annihilation of matter and antimatter might be the only events that break the cosmic stillness, brief flashes of energy in an otherwise empty and silent universe. But maybe the most profound lesson that antimatter teaches us about endings is that they're not really endings at all. In the quantum realm, particles are constantly being created and destroyed, transformed from one form to another, recycled through the fundamental processes of nature. The antimatter that annihilates today might be recreated tomorrow through vacuum fluctuations or black hole evaporation. This perspective transforms our understanding of cosmic endings. Instead of seeing the universe's far future as a time of decay and death, we might see it as a time of transformation and renewal. The matter that makes up stars and planets and people doesn't disappear, it changes form, becoming antimatter, becoming energy, becoming part of the quantum foam that underlies all existence. In this view, antimatter isn't just a dangerous substance or a cosmic mystery, it's a reminder that the universe is fundamentally creative, constantly reinventing itself through processes that span the smallest and largest scales of existence. Every annihilation is also a creation. Every ending is also a beginning. As you close your eyes tonight, remember that the story of antimatter is still being written. In laboratories around the world, scientists are creating new antimatter particles, probing their properties, and slowly unraveling their secrets. In the depths of space, cosmic rays are producing antimatter in stellar explosions and galactic collisions. In the quantum vacuum, matter and antimatter are dancing their eternal dance of creation and annihilation. The most dangerous substance in the universe might also be the key to understanding the universe's deepest mysteries, the nature of time, the structure of space, the meaning of existence itself. And in that possibility we find not an ending, but a beginning, the start of a new chapter in humanity's eternal quest to understand the cosmos and our place within it. The last particle of antimatter might be the first clue to secrets we haven't even learned to ask about yet. And in that beautiful uncertainty, the universe continues its greatest magic trick, transforming the familiar into the mysterious, the known into the unknown, the ending into the beginning of something wonderful and strange, and utterly beyond our current imagination.